Chapter 15, Part 2 of Volume 2 of Airplane Flying Handbook, FAA-H-8083-3A. This is a LibriVox recording. All LibriVox recordings are in the public domain. For more information or to volunteer, please visit LibriVox.org. Recording by Jairus Amar. Airplane Flying Handbook by the FAA. Chapter 15. Speed Margins. The typical piston-powered airplane had to deal with two maximum operating speeds, V and O, maximum structural cruising speed, represented on the airspeed indicator by the upper limit of the green arc. It is, however, permissible to exceed V and O and to operate in the caution range, yellow arc, in certain flight conditions. V and E. Never exceed speed, represented by a red line on the airspeed indicator. These speed margins in the piston airplanes were never of much concern during normal operations because the high drag factors and relatively low cruise power settings kept speeds well below these maximum limits. Maximum speeds in jet airplanes are expressed differently, and always define the maximum operating speed of the airplane, which is comparable to the V and E of the piston airplane. These maximum speeds in a jet airplane are referred to as VMO, maximum operating speed expressed in terms of knots; MMO, maximum operating speed expressed in terms of a decimal of Mach speed, speed of sound. To observe both limits VMO and MMO, the pilot of a jet airplane needs both an airspeed indicator and a Mach meter, each with appropriate red lines. In some general aviation jet airplanes, these are combined into a single instrument that contains a pair of concentric indicators, one for the indicated airspeed and the other for indicated Mach number. Each is provided with an appropriate red line. See Figure 15-8. A more sophisticated indicator is used on most jetliners. It looks much like a conventional airspeed indicator, but has a barber pole that automatically moves so as to display the applicable speed limit at all times. Because of the higher available thrust and very low drag design, the jet airplane can very easily exceed its speed margin, even in cruising flight, and in fact in some airplanes, in a shallow climb. The handling qualities in a jet can change drastically when the maximum operating speeds are exceeded. High-speed airplanes designed for subsonic flight are limited to some Mach number below the speed of sound, to avoid the formation of shock waves that begin to develop as the airplane nears Mach 1.0. These shock waves, and the adverse effects associated with them, can occur when the airplane speed is substantially below Mach 1.0. The Mach speed at which some portion of the airflow over the wing first equals Mach 1.0 is termed the critical Mach number, Mach crit. This is also the speed at which a shock wave first appears on the airplane. There is no particular problem associated with the acceleration of the airflow up to the point where Mach 1.0 is encountered. However, a shock wave is formed at the point where the airflow suddenly returns to subsonic flow. This shock wave becomes more severe and moves aft on the wing as speed of the wing is increased, and eventually flow separation occurs behind the well-developed shock wave. See Figure 15-9. If allowed to progress well beyond the MMO for the airplane, this separation of air behind the shock wave can result in severe buffeting and possible loss of control, or upset. Because of the changing center of lift of the wing, resulting from the movement of the shock wave, the pilot will experience pitch change tendencies as the airplane moves through the transonic speeds up to and exceeding MMO. See Figure 15-10. For example, as the graph in Figure 15-10 illustrates. Initially, as speed is increased up to Mach 0.72, the wing develops an increasing amount of lift, requiring a nose-down force or trim to maintain level flight. With increased speed and the aft movement of the shock wave, the wing's center of pressure also moves aft, causing the start of a nose-down tendency, or tuck. By Mach 0.83, the nose-down forces are well developed to a point where a total of 70 pounds of back pressure are required to hold the nose up. If allowed to progress unchecked, Mach tuck may eventually occur. Although Mach tuck develops gradually, if it is allowed to progress significantly, the center of pressure can move so far rear-wind that there is no longer enough elevator authority available to counteract it, and the airplane could enter a steep, sometimes unrecoverable dive. An alert pilot would have observed the high airspeed indications, experienced the onset of buffeting, and responded to aural warning devices long before encountering the extreme stick forces shown. However, in the event that corrective action is not taken and the nose allowed to drop, increasing airspeed even further, the situation could rapidly become dangerous. As the Mach speed increases beyond the airplane's MMO, the effects of flow separation and turbulence behind the shockwave become more severe. Eventually, the most powerful forces causing Mach tuck are a result of the buffeting and lack of effective downwash on the horizontal stabilizer because of the disturbed airflow over the wing. This is the primary reason for the development of the T-tail configuration on some jet airplanes, which places the horizontal stabilizer as far as practical from the turbulence of the wings. Also, because of the critical aspects of high altitude/high Mach flight, most jet airplanes capable of operating in the Mach speed ranges are designed with some form of trim and autopilot Mach compensating device, stick puller, to alert the pilot to inadvertent excursions beyond its certificated MMO. Recovery from overspeed conditions. The simplest remedy for an overspeed condition is to ensure that the situation never occurs in the first place. For this reason, the pilot must be aware of all the conditions that could lead to exceeding the airplane's maximum operating speeds. Good attitude instrument flying skills and good power control are essential. The pilot should be aware of the symptoms that will be experienced in the particular airplane as the VMO or MMO is being approached. These may include nose-down tendency and need for back pressure or trim, mild buffeting as airflow separation begins to occur after critical Mach speed, actuation of an aural warning device/stick puller at or just slightly beyond VMO or MMO. The pilot's response to an overspeed condition should be to immediately slow the airplane by reducing the power to flight idle. It will also help to smoothly and easily raise the pitch attitude to help dissipate speed. In fact, this is done automatically through the stick puller device when the high speed warning system is activated. The use of speed brakes can also aid in slowing the airplane. If, however, the nose-down stick forces have progressed to the extent that they are excessive, some speed brakes will tend to further aggravate the nose-down tendency. Under most conditions, this additional pitch downforce is easily controllable, and since speed brakes can normally be used at any speed, they are a very real asset. A final option would be to extend the landing gear. This will create enormous drag and possibly some nose-up pitch, but there is usually little risk of damage to the gear itself. The pilot transitioning into jet airplanes must be familiar with the manufacturer's recommended procedures for dealing with overspeed conditions, contained in the FAA-approved Airplane Flight Manual for the particular make and model airplane. Mach buffet boundaries. Thus far, only the Mach buffet that results from excessive speed has been addressed. The transitioning pilot, however, should be aware that the Mach buffet is a function of the speed of the airflow over the wing, not necessarily the airspeed of the airplane. Any time that too great a lift demand is made on the wing, whether from too fast an airspeed or from too high an angle of attack near the MMO, the high-speed buffet will occur. However, there are occasions when the buffet can be experienced at much slower speeds, known as low-speed Mach buffet. The most likely situations that could cause the low-speed buffet would be when an airplane is flown at too slow a speed for its weight and altitude, causing a high angle of attack. This very high angle of attack would have the same effect of increasing airflow over the upper surface of the wing, to the point that all of the same effects of the shockwaves and buffet would occur as in the high-speed buffet situation. The angle of attack of the wing has the greatest effect on inducing the Mach buffet at either the high or low speed boundaries for the airplane. The conditions that increase the angle of attack, hence the speed of the airflow over the wing and chances of Mach buffet, are high altitudes. The higher the airplane flies, the thinner the air, and the greater the angle of attack required to produce the lift needed to maintain level flight. Heavy weights. The heavier the airplane, the greater the lift required of the wing, and all other things being equal, the greater the angle of attack. G-loading. An increase in the G-loading of the wing results in the same situation as increasing the weight of the airplane. It makes no difference whether the increase in G-forces is caused by a turn, rough control usage, or turbulence. The effect of increasing the wing's angle of attack is the same. An airplane's indicated airspeed decreases in relation to the true airspeed as altitude increases. As the indicated airspeed decreases with altitude, it progressively merges with the low-speed buffet boundary, where pre-stall buffet occurs for the airplane at a load factor of 1.0 g. The point where the high-speed Mach indicated airspeed and low-speed buffet boundary indicated airspeed merge is the airplane's absolute or aerodynamic ceiling. Once an airplane has reached its aerodynamic ceiling, which is higher than the altitude stipulated in the FAA-approved Airplane Flight Manual, the airplane could neither be made to go faster without activating the design stick puller at Mach limit, nor can it be made to go slower without activating the stick shaker or stick pusher. This critical area of the airplane's flight envelope is known as coffin corner. Mach buffet occurs as a result of supersonic airflow on the wing. Stall buffet occurs at angles of attack that produce airflow disturbances, burbling, over the upper surface of the wing, which decreases lift. As density altitude increases, the angle of attack that is required to produce an airflow disturbance over the top of the wing is reduced until the density altitude is reached, where Mach buffet and stall buffet converge. Coffin corner. When this phenomenon is encountered, serious consequences may result, causing loss of airplane control. Increasing either gross weight or load factor, G factor, will increase the low-speed buffet and decrease Mach buffet speeds. A typical jet airplane flying at 51,000 feet altitude at 1.0 g may encounter Mach buffet slightly above the airplane's MMO, 0.82 Mach, and low-speed buffet at 0.60 Mach. However, only 1.4 g, an increase of only 0.4 g, may bring on buffet at the optimum speed of 0.73 Mach, and any change in airspeed, bank angle, or gust loading may reduce this straight and level flight 1.4 g protection to no protection at all. Consequently, a maximum cruising flight altitude must be selected which will allow sufficient buffet margins for necessary maneuvering and for gust conditions likely to be encountered. Therefore, it is important for pilots to be familiar with the use of charts showing cruise maneuver and buffet limits. See Figure 15-11. The transitioning pilot must bear in mind that the maneuverability of the jet airplane is particularly critical, especially at the high altitudes. Some jet airplanes have a very narrow span between the high and low speed buffets. One airspeed that the pilot should have firmly fixed in memory is the manufacturer's recommended gust penetration speed for the particular make and model airplane. This speed is normally the speed that would give the greatest margin between the high and low speed buffets, and may be considerably higher than design maneuvering speed, VA. This means that, unlike piston airplanes, there are times when a jet airplane should be flown in excess of VA during encounters with turbulence. Pilots operating airplanes at high speeds must be adequately trained to operate them safely. This training cannot be complete until pilots are thoroughly educated in the critical aspects of the aerodynamic factors pertinent to mock flight at high altitudes. End of Chapter 15, Part 2. Recording by Jairus Amar.